Hello, we're glad you've joined us for this live webinar, Vitamin D Measurements, Facts We May Not Want to Know. I am Judy O'Rourke of LabRoots, and I'll be moderating this session. Today's educational web seminar is presented by LabRoots, the leading scientific social networking website and provider of virtual events and webinars advancing scientific collaboration and learning. It's brought to you by Sciex. Sciex helps to improve the world we live in by enabling scientists and laboratory analysts to find answers to the complex analytical challenges they face. To learn more about Sciex, please visit sciex.com. Let's get started. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. You can pose questions to the speakers during the presentation while they're fresh in your mind. To do so, simply type them in the Q&A box, which will open when you click the green Q&A button at the lower left of the presentation window. Questions will be answered after the presentation. To enlarge the slide window, click on the screen icon in the lower right-hand corner of the slide window. If you experience any technical problems seeing or hearing the presentation, just click on the support button found at the top right of the presentation window, or report your problem by clicking on the green Q&A button at lower left. I now present Karla Gonye, the Global Director of Product Marketing for the Sciex Clinical Division, who will give a brief presentation. She is responsible for new product launches, including Sciex mass spectrometers, clinical assays, and mass spec accessories for the global business with a focus on the Americas, Europe, China, and Asia Pacific. She is based in Framingham, Massachusetts. Hand it over to you, Karla.
Okay, great. Thank you, Judy. Thank you for the introduction, and thank you to all the participants for taking the time to join us today. I will provide just a brief introduction to Sciex and our latest product innovations, as we are all eager to hear this intriguing talk by Dr. Gary Horowitz. As many of you know, Sciex is a global leader in mass spectrometry in the life sciences industry, and we've recently launched the TOPAZ system at AACC this year. The TOPAZ system is an FDA-reviewed, fully integrated platform with an IVD assay driven by our intuitive software ClearCore, which is designed specifically for use in the clinical labs. The TOPAZ system is known as Mass Spec Made Simple, a system that's easy to learn and validate in the clinical lab with a CDC-certified de novo FDA-granted vitamin D assay, which I'll show on this next slide. The availability of this new assay kit will enable clinical labs to expand their in-house testing services, as well as add their own laboratory-developed tests, LDTs, on the TOPAZ system with its open and closed design. And we hope you will be more empowered to do more, save more, and deliver more competent results to support clinicians and physicians. So we're very excited that Sciex is uniquely poised to deliver this CDC-certified assay to address a growing demand within the hospital laboratory marketplace to reduce costs and send out, particularly with high-volume assays like vitamin D. So thank you, and hope you enjoy the program. And back to you, Judy.
Thank you, Karla, for your overview. I now present today's speaker, Gary Horowitz, MD. Dr. Horowitz is the Medical Director for Informatics and Point-of-Care Testing and the Associate Medical Director for Clinical Chemistry in the Department of Pathology and Laboratory Medicine at Tufts Medical Center. Dr. Horowitz received his medical degree from Harvard Medical School, completed a clinical pathology residency at Beth Israel Hospital, and later became the Director of Clinical Chemistry at Beth Israel. He was named Director of Clinical Chemistry at Beth Israel Deaconess Medical Center following the merger of Beth Israel and New England Deaconess Hospital. In 2017, he transferred to his current position at Tufts, where he also serves as a visiting associate professor of pathology and laboratory medicine at the Tufts University School of Medicine. Dr. Horowitz chaired the Chemistry Resource Committee of the College of American Pathologists from 2007 through 2010. He was reappointed as chair in 2012 and served in that role through 2016. He has been an active member of the CAP Accuracy-Based Committee and currently serves as its vice chair. Dr. Horowitz has also worked with the Clinical Laboratory Standards Institute, where he was chair of the working group on document C28 concerning reference intervals. He is now vice chair of the working group on document GP27 concerning proficiency testing. Dr. Horowitz's complete bio is found on the LabRoots website. Dr. Horowitz will now begin his presentation.
Thank you, Judy, for that very gracious introduction, and thank you, too, to Sciex, who made this presentation possible. Just to remind you, we're going to talk about vitamin D measurements today, facts we may not know, and in fact, facts we may not want to know. Let me start by mentioning some disclosures that you've already heard about. I am on the CAP, College of American Pathologists Chemistry Resource Committee, and the Accuracy-Based Testing Committee. The grant and research support for the studies that I will be talking to you about were provided by Sciex in terms of reagents for the Topaz LC-MS-MS method for vitamin D. And they also provided financial support to Beth Israel Deaconess Medical Center for participating in data submissions to the FDA on that assay. All of the author contributions that are mentioned here were done while all of the authors were at Beth Israel Deaconess Medical Center, where all of these studies were done. I'm going to start with the email, the index email that I received in November of 2012 from one of my colleagues in endocrinology. And I'll read it to you. It said, I had my second patient in recent weeks with completely intact GI tract, but taking 50,000 units weekly of vitamin D, who is still D insufficient. I must say that barring short gut or other issues, I've always had the impression that this robust amount should be plenty for patients with intact GI tract, and the published literature I am aware of supports this. So we started doing some troubleshooting to figure out what might be going on. We sent 3 potentially incorrect samples from our lab to 2 separate reference labs. And they were performing the assay by LC-MS-MS, whereas we were using an immunoassay. And those results indicated that there were some serious immunoassay under-recoveries of 25-hydroxy vitamin D2. When we calculated it out, it was roughly a 40% cross-reactivity, even though the package inserts from those immunoassays indicated cross-reactivities for D2 of close to 100%. At the time we sent those samples, one of the samples that we sent to the same labs actually had a result where the immunoassay result matched the LC-MS-MS result. And what was different about that sample was that its 25-hydroxy D2 concentration was low. So based on these initial studies and results, we sent an additional 20 samples for LC tandem mass spec evaluation. And we found that 3 of those samples had relatively high concentrations of D2, and we observed the same 40 to 50% cross-reactivity. So I will get into the details of the studies that we did, but let me, at this point, give you an outline for the presentation. I will talk a little bit about a clinical background for vitamin D, some of the physiology, then issues surrounding its measurement, the actual performance of many of those methods, and after I've told you about some of those problems, I'm going to tell you and share with you some of the thoughts I have about solutions to those issues that may come up. Let me start also by saying the goals of my presentation are on this slide. Number 1, the goal of my presentation is not to convince you to buy a mass spectrometer if you already have one, if you don't already have one. Rather, the goal is to help you understand the potential limitations of your immunoassays. I'd like to point out that in a recent CAP proficiency testing survey, only 28 of almost 1,600 labs were using LC-MS-MS for 25-hydroxy vitamin D. In other words, 98% of these 1,600 labs are not using mass spectrometry. For those of us who are using immunoassays, we need to know how to inform our physicians of potential assay limitations. And that's really the goal of this presentation today. We're going to use the tools of mass spectrometry and the newly FDA-cleared assay from Sciex to investigate the performance of the 3 immunoassays we had access to at Beth Israel Deaconess Medical Center. So let's talk about the background on the clinical background on vitamin D. The advertising, as many of you know, is that vitamin D is the cure for everything, that it will work for osteoporosis, and some people argue that it will work for cancer. It's everywhere. The facts are, however, that in temperate climates, much of the United States that is, in the absence of taking vitamin D supplements, most people are probably vitamin D deficient. In other words, we don't need a lab test to tell us that people are vitamin D deficient. A little more background. Osteoporosis is a serious and common problem. Many people in the United States, at least, have been taking supplements of calcium and vitamin D to prevent it, both calcium and vitamin D. With 20/20 hindsight, in retrospect, we realized that the calcium supplementation was probably not necessary. The problem, instead, has always been too little vitamin D. In the past, and even recently, it's not much higher than this, the official recommended daily allowance of vitamin D was 400 IUs per day. And it's clear now that that's not adequate. People probably need as much as 1,000, if not 2,000 IUs per day. Vitamin D testing is rarely needed. At Beth Israel Deaconess, we were doing, at the time we did these studies, about 150 vitamin D assays per weekdays. And as I said a slide or two ago, most people in temperate regions, much of the United States, are deficient. So you don't need the lab test to tell you that you should be taking a supplement of vitamin D, 1,000 to 2,000 units per day. And yet, we were receiving 150 vitamin D assays per weekday. So why are we doing so many vitamin D tests? Well, the first thing is that there are many diseases associated with low vitamin D concentrations. I've underlined the word associated because there's no cause and effect relationship that's been established. But those associated conditions are cardiovascular disease, cancer, as I mentioned earlier, fractures, and even mortality. And then there are conditions that are alleged to benefit, again underlining alleged to benefit because there's no scientific evidence that it actually works, but conditions alleged to benefit from adequate vitamin D concentrations. A whole series of autoimmune diseases, including diabetes, multiple sclerosis, rheumatoid arthritis, Crohn's, hypertension, heart disease and stroke, upper respiratory tract infections, wheezing and asthma, and even falling. And as listed here on the right-hand side of the slide, there was an article this past April in the New York Times talking about why are so many people popping vitamin D. So we've seen, all clinical laboratories have seen, a sustained increase in the testing volumes. And that should be especially notable in light of the fact that there is no national primary care professional organization that recommends population-wide screening. Rather, the suggestions to maintain one's vitamin D sufficiency include sensible sun exposure, vitamin D fortification of foods. You've all seen this in the grocery stores. Many products are now fortified with vitamin D, not just milk, and over-the-counter supplementation. Again, that 1,000 to 2,000 units per day. Nonetheless, the testing volumes have increased substantially. In the chart to the right-hand side of the slide, you'll see a graphical demonstration about the Medicare volume. Over the course of 10 years, from 2000 to 2010, the Medicare volume of 25-hydroxyvitamin Ds increased 83-fold. It's an unbelievable increase. The CDC noted that commercial payers have seen a 2.5-fold increase in the 5-year span from 2009 to 2014. And perhaps most striking in some respects, in a survey of 800,000 Maine residents in a 3-year period, 20% had at least one vitamin D determination. So it's become incredibly common to have vitamin D levels measured. Now, it's not as though there's never a reason to do vitamin D testing. There are some specific scenarios where vitamin D testing is appropriate. And as shown on this slide, they include poor bone health, malabsorption syndromes, increased vitamin D metabolism, decreased production of 25-hydroxyvitamin D, so that even if you're getting vitamin D, you're not going to be able to make the 25-hydroxyvitamin D, altered production of the metabolite of 25-hydroxyvitamin D, 125, which occurs in chronic kidney disease and some granulomatous diseases like sarcoidosis, and some medications. So in these circumstances, it is appropriate to do vitamin D testing, but these are not common syndromes. Let's talk briefly about vitamin D metabolism. Vitamin D is made in the skin, or it's ingested in food. It receives a single hydroxylation in the liver to form 25-hydroxyvitamin D, and then it gets an additional hydroxylation in the kidney, forming 125-dihydroxyvitamin D. So the pathway is summarized in the 4th bullet. Vitamin D goes to 25-hydroxyvitamin D, and then to 125-dihydroxyvitamin D. All of the experts are in agreement that to monitor dietary adequacy, the analyte that we should be measuring is 25-hydroxyvitamin D. And I've already done it, but I may do it again. When I'm talking about vitamin D, I'm usually talking about 25-hydroxyvitamin D. That's the analyte that laboratories measure. Moving on to the measurement of 25-hydroxyvitamin D, there are 2 basic methodologic principles. There's chromatography, mass spectrometry, typically liquid chromatography, tandem mass spectrometry, and the second methods are immunoassay based. Those are the 2 basic flavors of vitamin D measurements. There are some issues that we should talk about in terms of the measurement that affect the measurement that are shown on this slide. There are, in fact, 2 major forms of vitamin D, cholecalciferol, which is D3, and that form of vitamin D is found in mammals, and ergocalciferol, that's vitamin D2, and that's found principally in plants. So you can see the structures here on the right. The difference, having a little trouble with my pointer, the difference is located in the circle here, and there's basically an extra methyl group up here. So there is a difference in mass because of that extra methyl group, and therefore mass spectrometry can distinguish D2 and D3 pretty easily because the masses of the 2 compounds are different. On the other hand, mass spectrometry cannot distinguish the epimers, and in the second part, the second image on the right-hand side of the slide, you'll see that the epimer basically is a hydroxyl group that is either below or above the ring structure at the bottom of the molecule. Since those epimers have exactly the same molecular weight, mass spectrometry cannot separate them. They will be conjoined on those assays. In order to distinguish the epimers from the other compounds, you need to do a chromatographic separation, which is illustrated in the bottom part of that second image. Immunoassays, in contrast to the mass spectrometers, do not distinguish D2 and D3. They typically cannot distinguish them and report only a total vitamin D. As long as the antibodies that are used in those immunoassays have 100% cross-reactivity to both D2 and D3, there is no problem with reporting the total vitamin D result. Because you may not need to know how much is D2 and how much is D3. What you need to know is what the total vitamin D is. So immunoassays that do have 100% cross-reactivity or close to it with both D2 and D3 can provide an acceptable total vitamin D result. Unfortunately, that's not the case with all the assays, and you'll see that data in a few minutes. Depending on the specific immunoassay that's used, you can make serious errors in assessing the total 25-hydroxy vitamin D concentration because you're not getting an adequate concentration of the D2 result. So remember, I want to have you recall that 98% of the clinical laboratories reporting data to the College of American Pathologists proficiency surveys are using immunoassays. And therefore, depending on how well those antibodies react with both D2 and D3, there could be a problem. So another complexity about vitamin D testing is that there are two ways of defining deficiency. Originally, the Institute of Medicine, considering only the bone health effects of vitamin D, defined deficiency as less than 20 nanograms per ml. And sufficiency was 20 to 60 nanograms per ml. And the reason they made those decisions on limits was that if you look here at the graph on the right-hand side of the slide, which has 25-hydroxy vitamin D total on the x-axis and the parathyroid hormone concentration on the y-axis, you can see that as your vitamin D level decreases, your PTH level will increase. And that's because at lower levels of 25-hydroxy vitamin D, your calcium may start to fall, and your parathyroid glands will start to put out more parathyroid hormone to help maintain your calcium concentration. So that's a sign of deficiency. And oops, I apologize. Let me get back to the right slide. As you become sufficient, following this arrow, at about 20, the PTH concentration, the parathyroid concentration, normalizes. And that was the reason that the Institute of Medicine said a level of 20 represents vitamin D sufficiency. And levels below 20, where the PTH level starts to increase, represent a problem. And that your parathyroids are having to supplement your calcium concentrations. Along came the Endocrine Society, which came out with slightly different guidelines. They maintained deficiency at less than 20, but they defined a new category called insufficiency, that levels between 21 and 29 nanograms per ml were considered by them to be insufficient, and one didn't reach sufficiency until you got to 30. And that's been a fairly controversial decision because, as we'll see on the next slide, raising the threshold for sufficiency had the effect, as noted in this publication, it resulted in almost half the tested population in this large Midwestern hospital as being vitamin D deficient. So there are a lot of people who have concentrations between 20 and 30 nanograms per ml, who previously, or using the Institute of Medicine guidelines, would have been considered sufficient, but using the Endocrine Society guidelines were now considered insufficient. Half the people who were getting vitamin D levels drawn. Okay, let's talk now about why accuracy is so important with vitamin D. When physicians use national or international guidelines, labs don't have the luxury of establishing their own reference intervals, commonly called normal ranges. Rather, the test results that we generate must match the reference method because those are the guidelines that the doctors will be following. We have many examples in the clinical lab where our results must be accurate, where we cannot define our own reference intervals. And a few of those examples are cholesterol and the related lipids. Those are all mandated by a variety of federal programs to have levels below specific thresholds. Hemoglobin A1C, again, has to be interpreted according to the national and international guidelines. Testosterone, again, guidelines for interpretation assume that you're going to get accurate results. And as we've just seen, even though the Institute of Medicine and the Endocrine Society have different guidelines, they both are using specific cut points that require that the results we generate be accurate. You can't define your own reference intervals. Your vitamin D levels have to be accurate. In an effort to achieve that accuracy, in November of 2010, a vitamin D standardization program was initiated by the CDC, and the Ghent University Reference Measurement Procedures became widely used as the reference method in comparison studies. NIST and CDC provided standard reference materials to help manufacturers and laboratories make sure their methods were accurate. Of note, as you'll see in a moment, there were only 10 of the 40 samples that were these reference materials contained detectable D2. Only 10 of the 40 contained any D2, and only one of the 40 had an appreciable D2 concentration of roughly 13 nanograms per mil. There are some proficiency testing services that provide an accuracy-based comparison. There's the DEQAS survey out of England, and the CAP has an accuracy-based vitamin D survey. And in these cases, there are commutable, genuine human serum samples provided, along with reference values to compare to. And as a result of those accuracy-based surveys and reference principle measurements to compare to, the imprecision across the methods has decreased from more than 30% interlaboratory variability down to 15% in 2011. That's the good news. It turns out, though, very, very few of those samples contain appreciable D2 concentrations. So let's talk a little bit about the advantages and disadvantages of these methods. On the left-hand side, we have LC tandem mass spec, and on the right-hand side, immunoassay. So LC mass spec is usually much slower throughput, but for vitamin D assays, there's really no need for fast turnaround time. Doctors can certainly wait to get their results until the next day. On the LC mass spec side, there may be problems distinguishing the epimers, which we talked about before. They have the same molecular weight, and distinguishing them requires chromatographic separation. On the immunoassay side, there's the problem of the D2 cross-reactivity and how close to 100% it is. LC mass spec assays, until the recent introduction of the Sciex method that was mentioned at the outset, are always laboratory-developed tests. So each laboratory will develop its own method, and it turns out in all of these accuracy-based surveys, there's a lot more lab-to-lab variation because of the fact that these are laboratory-developed tests, and there's not as much standardization as there needs to be. On the other hand, the immunoassays are FDA cleared. There's a lot less lab-to-lab variation within those methods because people are running them according to the manufacturer's recommendations. Having said that, on average, LC mass spec is much closer to the true value, whether you're looking at the DEQAS surveys or the CAP accuracy-based surveys. The LC mass spec values are almost always closer to the true values from the reference method procedures. And the immunoassays, the accuracy varies a significant amount depending on the manufacturer. And I will show you some slides about that going forward. Again, I want to call your attention to the fact that the overwhelming majority of laboratories are not using LC mass spec. They're using immunoassay. So a caution here, and it's one that I make many times to many people. Just because you use the reference method principle, in this case liquid chromatography, tandem mass spectrometry, it doesn't mean you're going to get accurate results. And that's because individual laboratories are developing these methods on their own, and it turns out not everybody is as proficient at mass spectrometry and liquid chromatography as they should be. And on the immunoassay side, just because you get the same results as your peers, which is usually how proficiency testing is graded, just because you get the same results as your peers doesn't mean you're getting accurate results. Typically there is this good interlaboratory agreement, but it could be wrong. So here's some information about the LC mass spec methods that I alluded to earlier. These two quotes come from the two accuracy-based surveys, CAP and DEQAS. And in both cases, I won't read these to you, but in both cases, it's recognized that most of the LC mass spec methods do not resolve the epimers. The majority of mass spec methods will, in fact, fail to resolve the three epimers of D2 and D3, and therefore they tend to run a little bit higher on the accuracy-based surveys, and that's a potential problem. A note on this epimer. The epimer is biologically inactive, which is why you don't want to include it in your assessment of 25-hydroxyvitamin D. It's found principally in samples from neonates, in whom it can be extremely high, in fact, but it can also be seen in samples from adults. So the best way to deal with it, and this is how it's dealt with in the reference method, and as you'll see later, this is how it's dealt with in the Sciex Topaz method. The epimers are separated out and not included in the total 25-hydroxyvitamin D. That's the right way to do it. Okay, some real data from my lab at Beth Israel Deaconess Medical Center. This will be easier to read in a second. I'm going to blow these up a little bit. These are results from the CAP accuracy-based vitamin D survey. Again, commutable material from April 2012. If you look a little carefully, you can see that 4 of the 5 challenges, there were 5 samples here, we have a little red mark that says 4 of our 5 measurements were unacceptable. We flunked the survey. Now you see it a little bigger on the slide. Our result on the first sample was 15. There were 60 labs in this peer group. The peer group mean was 15, and we were right on the mean value, so our standard deviation index was 0. Similarly, 18, 18, perfectly matched the mean of our peer group. 25 versus 28, still very close to the peer group mean. 13 was our result versus 14 for the peer group, 8 versus 9. According to our peer group, we were doing wonderfully. The problem is that when we looked at the true value based on the reference method principle, our values were awful. The true value was 29.4. Our value was 15. and you can read the rest. They were all pretty awful. Acceptable, and I'm going to come back to this later, acceptable on these surveys is that you have to be only within 25% of the true value. That's a pretty wide bar for modern laboratory testing. But even with a bar as wide as plus or minus 25% of the true value, we flunked 4 of the 5 measurements. Now on these accuracy-based surveys, the CAP includes the following explanation. You should first compare your laboratory's results to the true values above, and the purpose of the comparisons is to show you whether observed differences are local to your laboratory or are also seen by other users of your method. So in our case, we were matching our peer group perfectly, but the whole peer group was incorrect. And that's what it says at the end here. For example, if you have a value close to the mean by your peer group, but very different from the true value, that probably reflects a problem with the peer group method, rather than the way your lab is running the assay. Here's another example. This is the DEQAS, the other accuracy-based survey. Again, commutable materials. This was from January of 2013. I'm only going to show you 2 of the 5 samples. And in this chart on the left-hand side of the slide, you have a variety of methods in different colors. And the target value for this sample was 23.4 nanograms per mil, represented by the horizontal turquoise or blue bar. And you can see that most of the, just as an explanation here, the units that they use in Europe are the nanomoles per liter. That's 58.5 nanomoles per liter. You can see that most of the methods were pretty good. Not perfect, but well within 25% certainly. But watch what happened on another sample from that same set of samples. This was a sample that had an admixture of D2 and D3. And now you see a very interesting phenomenon. Many of the assays, these are all different immunoassays, except for the LCM-SMS, which is the bright purple value here. Again, truth is the horizontal blue or turquoise line. Mass spec was beautiful. But the other methods were variable in how accurate they were. And in this particular one that I've highlighted, the purple, the light purple, if you assume 100% D3 cross-reactivity, which is pretty accurate for this method at least, the most left-hand one, the apparent D2 cross-reactivity is only 38%. I'm going to come back to this again later, so let me explain it here. Since we know on this, on sample 429, that the light purple method got pretty much exactly 100%, then we can assume that it got 19.1 for the D3 in sample 430. So if you take that value and subtract it from their total value, you can calculate what the D2 cross-reactivity is. And when you do that, it's 38%. That will become clearer, I hope, as we go forward. Now, in the United States, there's a available by prescription high-dose vitamin D. It turns out the only high-dose vitamin D available by prescription in the United States is 50,000 IUs, and it's vitamin D2 exclusively. There is no equivalent vitamin D3. And this is from a publication telling you the circumstances in which doctors can use high-dose vitamin D2 to supplement patients who otherwise are not going to absorb or manufacture sufficient vitamin D. And I've highlighted them with red boxes here. And you can see these are pretty unusual circumstances and rare diseases. But in these cases, you need to use more vitamin D than you can take orally easily. And even if you want to take them orally, to get a dose that high, you've got to get the prescription. Now, the one bullet point I haven't put a red box around, I will highlight now. For some reason, it was decided that you could treat, I will call garden variety vitamin D deficiency, with 50,000 units of vitamin D2. You give it recommended orally every week for 8 to 12 weeks, and you can repeat it for another 8 to 12 weeks if necessary. And it was this indication that I think started doctors prescribing vitamin D2 in high doses. Rather than taking a longer time to give them 1,000 units or 2,000 units over the counter per day, they went with the 50,000 units prescription D2. In all of these cases, the vitamin D testing is needed and it must be accurate. This is not screening anymore. This is people with serious vitamin D deficiencies, and you want to make sure that your therapy is working. So now to the study that we did. It was the evaluation of 3 high-throughput immunoassay analyzers for 25-hydroxyvitamin D. I told you already that Beth Israel Deaconess routinely receives 150 to 200 samples every weekday, almost exclusively from outpatients, hospital clinics, and affiliated physicians' offices. For the purpose of this talk today, I'm not going to identify the methods by name. We're just going to look at them as A, B, and C, because the points I'm trying to make are generic. The reference method that we used is the Sciex vitamin D assay on the Topaz system, which is traceable to the CDC Ghent University reference measurement procedure, and it is CDC certified by the VDSCP program. Now, at the time we did this study, as I mentioned in passing at the outset, we were collecting data for Sciex for their FDA submission. Dr. Tolan, my colleague, was working on the project, and that was the reason we had the Topaz system and what we were running on it. We had been trying, to investigate this vitamin D2 problem for many years, but we hadn't had much luck doing it because we didn't have our own mass spec method. So Dr. Tolan asked the people from Sciex if, during the course of our validation of that method, if we could use their system to do our research protocol. And Sciex was nice enough to let us do the studies I'm about to show you. So as you saw, the index case was in 2012. We tried many times to get things going in a variety of different committees, but it just never seemed to work for one reason or another. And I'm very glad that Dr. Tolan thought of using the Sciex system and that Sciex was willing to support us so that we could finally get a really good sense of what was going on with the various immunoassays. So without further ado, let's go into what we did. We did a method, it was 2 phases of the study, method comparison with 105 residual patient samples, and a prevalence study with 120 randomly selected samples. The article will appear later, I think early next year, in the Journal of Applied Lab Medicine. It was accepted in September, but I think it will appear online sooner. I don't have an exact date, but you'll be able to see it online. You're going to get to see it here first, though. The method comparison study is summarized here. You can see that we have the 4 methods, the LC tandem mass spec, our reference method, the Sciex method, critical to the study, and then we had 3 immunoassays that we were able to run. This slide demonstrates the distribution of all the samples we ran, and you can see the medians and the quartiles on this box and whisker plot. And then comparing those distributions, you can see that immunoassay A was not significantly different, but immunoassay B and C were statistically significantly different. Both of those distributions were lower. we will have more details coming up. Here is a more conventional correlation regression demonstration of the three assays. In all three of these graphs, the LC tandem mass spec values are on the x-axis. Again, these are traceable, these are accurate, and on the y-axis are the individual immunoassay results. What you can see here are the individual points. In light gray, a little difficult to see, perhaps, is the line of identity. The darker line is the best fit line for each of those assays. And the dashed lines that you can see are the 25% acceptable limits that are used by the proficiency testing. So any points that are outside those dashed lines are more than 25% from the reference method value. You can see that the first one, A, is pretty good. B is almost as good. C has a lot of points that are outside the acceptable limits. And you can see the regression lines here. Thiel-Sen regression is a robust regression method so that outliers don't inappropriately weigh the curve that you get. So consider it a more robust regression. The correlation coefficients you can read yourselves, but at the bottom, the third line down, the number of samples outside the 25% acceptable limits. And again, for laboratorians, I think 25% allowable variations from the true value is far too liberal. But even with that liberal margin, 24% of the samples were unacceptable for method A, 33% for method B, and fully 50% of the values were unacceptable for method C. Then we look at some bland Altman plots, difference plots. Here again on the x-axis you will see the LC tandem mass spec values. And on the y-axis, the difference between the total vitamin D by the individual assays subtracted from them the LC-MS-MS method. You can see that method A, there's some scatter around it as you get to higher concentrations, but they're pretty much close to, on average, 0. And that's reflected in the table at the bottom. The mean bias for method A was minus 0.7 with a standard deviation of 8.1. For B, it gets a little worse. The mean bias was 5.6, and for method C, it's 5.0. And then, this is perhaps the most interesting data, and the thing that the data I had hoped to get for many years. Dr. Tolan and I both were trying to get for many years, but here it is. We're now plotting the difference between the total 25-hydroxy vitamin D by each immunoassay, A, B, and C, on the y-axis. But now instead of plotting it against total LCMS 25-hydroxy, we're plotting it against the D2 25-hydroxy. What you can see is that at concentrations starting at about 10 or 20 nanograms per mil, each of the assays starts to fall apart a little bit in some cases and a lot in other cases. So for assay A, there's a slight over-recovery that increases with increasing concentration. B shows a decrease, a negative effect at higher concentrations, and C is an even more severe decrease with higher concentrations. We've added a second line to the table now. The mean bias for concentrations of D2 greater than 20 is 5.6 positive bias for A, minus 17.5 for B, and minus 20 for C. I mean, that is an amazing number when you think about it. You're talking about differences of roughly 20 nanograms per mil in vitamin D differences based on the D2 concentration. And those lines, those dashed lines for B and C, represent the mean bias. And your eyes are not deceiving you. Those are, in fact, roughly 20 nanograms per mil negative bias. We then took that data and we said, let's figure out what the cross-reactivity for these three immunoassays is. So if you, I'm going to try this pointer again. It's doing funny things, so I'm not going to use it. At the top of the slide, we talk about the estimated immunoassay D2 25-hydroxy concentration. The equation just below that, the way we get that number is that it's equal to the total immunoassay value that we get, subtracted from that what we know to be the D3 concentration from the mass spec. I alluded to this earlier in my talk. So if we assume 100% D3 cross-reactivity of the immunoassays, and we know what the D3 concentration is from the mass spec assay, we can use that number, subtract it from the total immunoassay result, and what remains would have to be the D2. So that gives us our estimated D2 concentrations. We've now graphed that value on the y-axis for A, B, and C, and you can see that in plot A, there is a distinct over-recovery of D2. In B, there's an under-recovery, and in C, there's another under-recovery. And you can see those slopes in the equations on the bottom, second row of the table. So the difference between the first row and the second row, one is the equation for regression for total vitamin D2, and the second is the regression for D2 vitamin, 25-hydroxy vitamin D. And the slopes are interesting. About 50% on B and C. A is 1.5, a 50% over-recovery, but it has a significant intercept, so it works out in principle to be somewhat less than that. Now we're going to do a cross-reactivity calculation by saying, let's take the 25-hydroxy vitamin D2 estimated, as we talked about in the previous slide, and compare it to the true 25-hydroxy vitamin D2, a number we know from the mass spec method. And when you do that, what you get is, let's look at the second row of the table that I've put here. The observed median value for assay A is 115%. The package insert says 105%. For assay B, the median concentration, cross-reactivity I should say, excuse me, the median cross-reactivity for vitamin D2 is 52%. The package insert says 92%. For C, observed 44%, package insert 82%. We never knew this true value until we were able to compare our samples to the reference, to a certified mass spec method, which is what we were able to do while we were doing the clinical trial with Sciex. So another question that came up is how frequently will these errors lead to clinical discordance? So we took 120 samples that we selected with a random number generated over 5 different days. We did that so that we weren't going to get patients from an endocrine clinic on one day and make things look worse than they really were. So we tried to spread this out over many different days over the course of a month, and we collected a total of 125 samples based on a random number generated, and figured out how many of them had D2 concentrations that were significant. 18% of the samples, 22 samples, contain more than 5 nanograms per mil of 25-hydroxy vitamin D2. Now, I don't know what it is in other populations around the country. Other hospitals may be different, but in Beth Israel Deaconess Medical Center, we had 18% of our samples selected at random with more than 5 nanograms per mil of 25-hydroxy-D2. And if you look at those points here, you can see that we're plotting here all of those values. Not surprisingly, A looks pretty good. B, you can see the negative bias, and C, you can see the negative bias. And now, if you look carefully, the dots that are, the circles that are filled in solid black are ones where there would be a clinical discordance. That is less than 30 nanograms per mil by immunoassay, but more than 30 nanograms per mil, excuse me, by mass spec. There were only 3 by method A, and there were 8 by B and C. Admittedly, some of these are right close to 30, so they're just on either side of that threshold, but some of them are pretty significant. I mean, these values here in the middle of slide B, where you see concentrations on panel B and C of 25-hydroxy vitamin D total of 40s and 50s, those, because of the low cross-reactivity, are going to look like values of 20 on immunoassays B and C. So, yes, there are a few that are right at the threshold, but there, again, are many that are significantly under-recovering, somewhat reminiscent of the index case that I read to you at the beginning, where the physician could not believe the patient wasn't responding. So these do have clinical consequences depending on your population and how many people have D2, as well as which particular assay you're using. So I just talked about this, that just replicating again that 22 contained more than 5 nanograms per mil, and 9 of them actually contained more than 20 nanograms per mil. These, again, are random samples. We had no idea what their concentrations were. We just took them based on a random number generator. And the mean biases were 6, positive 6, minus 17, and minus 20. So on these randomly selected samples, there were significant numbers of clinically inaccurate values. And we did a little calculation for Beth Israel Deaconess population at an annual volume of 37,500 tests, the calculations there, an 8% error rate, it hurts me to say this, an 8% error rate suggests that as many as 3,000 potential inaccuracies were reported per year. It's not a comforting thought. We're getting towards the end here. I wanted to emphasize that some of the things we're talking about actually have implications on clinical research and epidemiologic studies. I mean, it's bad enough that they have implications on individual patients, but this article, the references at the bottom of the slide, this article points out that differences can also have tremendous ramifications on epidemiologic studies. And what they pointed out is that based on using a cutoff value of 30 nanograms per mil, representing insufficiency, depending on which assay you used, you would say that either 8% of people are insufficient if you were using a mass spec method, 22% if you were using one particular radioimmunoassay, and 43% if you were using a chemiluminescent immunoassay. Again, I don't know the manufacturers. Manufacturers of these don't matter so much. It's the point that depending on which assay you use and how accurate it is, you can get strikingly different conclusions from your research studies that get into the literature. Okay, so I have told you about the fact that we may have problems, whether we're doing mass spec assays or whether we're doing immunoassays. And again, most of us are doing immunoassays. So I would feel terrible if I didn't share with you some of my thoughts about how we can improve the situation. I've given a lot of thought to this over the years because I've been plagued by this knowledge that I wasn't able to prove until recently, that there are issues with some of the immunoassays. So first and foremost, we can try to improve test utilization. We've already said that there are really no screening recommendations, but many physicians are ordering this test pretty much as a screening test. Word should get out that almost everyone in a temperate climate is deficient, and take vitamin D3 1 to 2,000 IUs per day. You don't need a lab test. You need to be aware of some assays' limitations. And again, this applies not to every assay, not to every mass spec assay, not to every immunoassay, but it will vary with the assay. You need to know whether you detect 25-hydroxy-D2 well or not. And you need to know whether you can separate and exclude the epimers if you're using either mass spec or, again, immunoassays, because these are all important constraints on these analytes. Specifically for people using immunoassays, you need to check what I would call the functional D2 cross-reactivity. As you've seen from our study, these may be very different from the package insert value. So I used to be comforted by the fact that I thought the assays had 100% or close to it cross-reactivity for D2, but it turns out they don't. Sometimes the manufacturers will tell you how their methods are certified or how they do well on proficiency testing surveys. Remember that those VDSP certification samples include only one sample with appreciable D2 concentrations. You need to be aware of the limitations of the accuracy-based surveys. Acceptable performance is within 25% of the target, and they have very, very few samples with appreciable D2 concentrations. So you really don't know how they're performing. And note that you can't tell from your immunoassay results whether a sample contains D2 or not. There's just no way to know from those assays. I think we should let physicians know from the clinical labs at the time they order the test that if 50,000 units of D2 is being prescribed, the LC mass spec methods are probably the preferred method. And I think lab reports should bear a footnote where appropriate, for some of these immunoassays at least, that the D2 recovery may be incorrect, so that they can call the lab and say, what can I do about that? For labs using LC tandem mass spec, again, note the limitations of the accuracy-based surveys. You want to know more than whether there's acceptable performance. You want to know whether there's really good performance and that they separate out the epimers. And that's the same point in number 2. And there are a lot of people, I think, that are probably hesitant to develop their own LDT, but maybe would like to do mass spectrometry based on the fact they'll get the right answer. And as of now, there is an FDA-cleared LC tandem mass spec method that meets all these requisite criteria. It will report a total 25-hydroxy vitamin D that excludes the epimers and includes just the D2 and the D3. And at the bottom of the slide, you can see the indications for use that were covered at the outset of this presentation. In closing, I'd like to acknowledge the contributions of 3 individuals, Dr. Nicole Tolan, Associate Medical Director at Clinical Chemistry when the study was done, and she's now moved on to be the Director of Scientific and Medical Affairs at Sciex Diagnostics. She did almost all the work for the study and deserves a lot of credit for persisting and helping me finally get to the bottom of the mysteries of the immunoassays. Edward Yoon was chief resident when he helped us put together the manuscript, and Ashley Brady is a lead technologist in pathology at Beth Israel Deaconess, and she was instrumental in helping us generate and collect a lot of the data. Again, I'd like to thank Sciex for supporting this study by providing materials for the LC tandem mass spec method. And with that, I want to thank you for your attention, and I think we may move on to questions, but I'm going to turn this back over to the moderator.
Thank you, Dr. Horowitz, for your presentation. A quick reminder for our audience on how to submit questions. Simply type them in the Q&A box found by clicking on the green Q&A button at the lower left of the presentation window. Dr. Horowitz will answer as many questions as time permits. And our first question is the CAP working to develop additional proficiency testing materials with appreciable D2, and what are some of the barriers to accomplishing this?
That's an excellent question, and the answer is yes. The CAP is trying to develop more samples with D2 concentrations that are appreciable, but it is difficult. It's fairly well known at this point that you can't just spike D2 into existing samples. There are some matrix effects that you introduce. The CAP has noticed that. DEQAS has noticed that. So the only way to get genuine commutable samples with appreciable D2 concentrations is to find people who are willing to take high doses of vitamin D2, and we've done that through IRB, with IRB approval. Basically, we screen people, and if their vitamin D levels are low, those people are then asked whether they're willing to participate, and they're given a dose of the 50,000 units of D2, and then they're drawn later to prepare the pools. So it's not an easy thing to do, but it's important that it be done. And so plans are to continue to offer periodically D2 containing commutable samples.
How much of the study depends upon the local population and their physician prescribing practices?
Another great question. The truth of the matter is that if everyone were taking just D3, we probably wouldn't have much of a problem. But in the old days, the vitamin D supplements were D2, and as I mentioned earlier on, originally the only preparation of high-dose vitamin D available in the United States, at least, was by prescription, and it was vitamin D2 only. And a lot of physicians were using that. Since then, people have started going to the internet and getting vitamin D supplements that are D3. They're now available by prescription in the U.S., I believe. But some physicians are still using the D2. So it really depends a lot on the local population, the local practices, and if we could get everyone just to take vitamin D3, this particular problem would not exist. But as we showed, at least at Beth Israel Deaconess, a lot of our physicians were prescribing vitamin D2. Fully 10% had levels of D2 that were greater than 20 nanograms per mil. And I'd like to just add again, there's no way to know if you're using an immunoassay what the practice is in your local hospital or your local population, which is why I recommended as one of the solutions to at least mention at the time of ordering and or with your report that if your patients, if a physician's patients are getting D2 supplementation, the immunoassay may not give you the best result.
If I am running vitamin D by immunoassay today and a physician is concerned about the accuracy of my result, what would you recommend for investigation?
Well, another good question, and one that I think I've dealt with more times than I'd like to think about. But the first thing one would do is I would repeat the assay just to make sure it wasn't a random assay. If there's any doubt about it, I would send it to a reference lab that's doing vitamin D by LC mass spec so that you get the D2 and D3. If you know that your assay, if you've convinced yourself or the manufacturer has told you that your immunoassay does detect both forms accurately, that may not be necessary. If you have your own LC tandem mass spec method where you know you're going to get the right answers for D2 and D3, that may not be necessary. But in general, I think when clinicians raise questions about any lab test that one runs, once you've proven that your result is reproducible, it's not a bad idea to send it somewhere else that will be done by a different method. And clearly the reference method for 25-hydroxy-vitamin D is liquid chromatography tandem mass spectrometry. So that would always be the final determinant for me.
Given 1,25-hydroxy is the functional form of vitamin D, is there an assay to differentiate 25-hydroxy from 1,25-hydroxy?
These are all really good questions. So there usually, in most cases, you don't need to measure 125 dihydroxyvitamin D, although in passing we talked about there are some disease conditions where 125, your 25-hydroxy may be adequate, but you're not able to convert it to 125. Chronic kidney disease comes to mind immediately. The other part of this question, though, is how does one know that your 25-hydroxy assay is not detecting 1,25 dihydroxy? And again, you'd have to rely on package inserts first, and our study didn't address that, so I can't give you any personal experience with it, but according to the package inserts for the immunoassays at least, the 125 does not appreciably cross-react with the immunoassay antibodies. I think the DEQAS survey has tried to look at some of the other metabolites, but I'd have to go back and look at the individual surveys to be sure about that. It's food for thought for an upcoming survey, I guess, or for an upcoming study, but we didn't address it. I don't think it's as big a problem unless you have patients with certain disease states. The 25-hydroxy is the preferred analyte for dietary and sufficiency. The 125 concentrations are much, much lower, but again, I'd have to, I don't want to give you a definitive answer because I really haven't studied it in great detail.
Okay. Karla, this next one is directed to you. Can the Sciex assay kit be used with an already established LC-MS-MS lab setup?
Hi, Judy. Thanks for the question. Actually, the vitamin D 200M assay was approved through the FDA for use with the TOPAZ system only. So we would consider that off-label, actually, and Sciex would not be able to support it. But if it's used with the TOPAZ system, we would provide support in setting up the assay on the TOPAZ system.
Thank you. Dr. Horowitz, now we're back to you. Have you tested or seen differences between serum and blood spot samples?
I have not personally tested blood spot samples. We've only looked at serum values in my lab.
Okay. Did your research look at the concentration of epimers and results between labs and methods?
Well, we didn't specifically look at the epimers. It's embedded in the correlation studies that I shared with you, but I don't remember offhand how many of our samples had appreciable epimer concentrations. It's possible, I guess, that some of the results, the differences that we saw, might be related to epimer. We know they're not included in the TOPAZ method from Sciex, and most of the immunoassays do not detect the epimers, but we didn't specifically look at it.
Are there issues with samples from patients who are dosed with vitamin D2, and wouldn't it be preferable to have Are there issues with samples from patients who are dosed with vitamin D2, and wouldn't it be preferable to have samples with higher endogenous D2 levels?
Well, that's an interesting question. The word endogenous is sort of complicated because mammals, humans, don't make their own D2. They are always ingesting it. So you're ingesting it from food sources or you're getting it from supplements. I think, though, that the issue that we face, as indicated by the index case, is that for physicians that are dosing patients with high-dose vitamin D2, the 50,000 units of D2, and these, remember, are patients who typically have fairly serious diseases, and now for physicians who choose to supplement patients with, as I called it earlier, garden variety vitamin D deficiency and not one of those diseases, if they're giving high-dose D2, then I think the best patients to look at are other patients who are getting high-dose D2. So the thing I said earlier about the way the CAP accuracy-based survey prepares samples exactly mimics what's being done therapeutically by physicians. So in this case, I think that that's actually the best way to simulate what's going on with real patient samples. So I understand where the question's coming from, and in general, I would think it's the correct way to think about it, but in this case, I'm not sure that it is. What we want to know is that if a physician is using high-dose D2, that we're going to recover the right value and not lead them on a wild goose chase to find out why his patient is not responding the way he expects, he or she expects, excuse me. I hope I made that clear. I do think that in this case, supplementing with high-dose D2 is exactly the right kind of sample to use.
Okay, and it looks like we have time for one more question. After developing a method for separating out the epimers on LC-MS, how would you recommend testing to ensure that the epimers are being separated?
Well, I think that ideally you'd have control material that would have epimers in it that would, tell you that your chromatographic separation is working. And then if there is any residual neonatal blood left over from other assays submitted to the lab, a large number of those samples will have epimers in them as well. But I would think that control material would be the way to go first.
Okay, and I would like to once again thank Dr. Horowitz for his presentation. Do you have any final comments?
I would just again encourage everyone, whether you're running LC mass spec or you're running immunoassays, to be aware of these subtleties of the pitfalls on both sides of both kinds of assays, and to deal with your clinical people and educate them. And sometimes the best way to educate them is not with a once-in-a-while newsletter or lecture, but as I indicated, to include in your reports and in your ordering requisitions some knowledge about what limitations might be, to encourage them to call if something doesn't make sense, and then, as I mentioned to one of the earlier questions, know how you're going to troubleshoot it when, in fact, those questions arise.
Well, thank you, Dr. Horowitz, and I'd like to thank the audience, too, for joining us today and for their interesting questions. Questions we did not have time for today will be addressed by the speaker via the contact information you provided at the time of registration. We'd also like to thank our sponsor, Sciex, for underwriting today's educational webcast. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. This webcast can be viewed on demand through April of 2018. LabRoots will alert you via email when it's available for replay, and we encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.